Good morning, ladies and gentlemen, and welcome to today's video. Today we'll talk about the chi-squared test of homogeneity, which is the second of the three types of chi-squared tests that we will be covering. Yesterday we talked about the chi-squared goodness of fit test, which, as a reminder, was essentially an expansion of a one proportion z-test. We had a population proportion distribution. We had one sample proportion distribution, and we were comparing that sample proportion to the population to see if the sample proportion distribution fit good with the population portion distribution. Things are slightly different in the chi-square test for homogeneity, and we will get right into it. Of course, brought to you by Couch Potato Brand Snack Food and Beverages. We sell food and beverages, nothing more. So let's motivate this topic with this question. High schools survey graduating classes to determine the plans of the graduates. We want to determine if the choices made by high school grads after high school has changed across the three graduating classes specified here. So that's 1980, 1990, and 2000. How would you classify this data? Do you think the choices have changed across the high school classes? Explain. Okay. So if this were a normal class, I would give you time to think about this and just basically break down this data however you want to make a decision. But really the official, more rigorous way to answer the question being asked is to run a hypothesis test. Namely, of course, the chi-squared test of homogeneity. But let's answer the first question. How would you classify this data? So, of course, there are two types of data, qualitative and quantitative. This is qualitative data, right? We have individuals that were asking questions, and they are answering those questions with some kind of a qualitative response. So, what did you do post-graduation? Military. What did you do? College, so on and so forth. So, and also along the vertical axis, you could see 1980, 1990, 2000. These are all categories that these people are being placed into. Okay, so this is categorical data, and it's very similar, really, to a two-proportion z-test because of the fact that we have what we're looking at here, 1980, this is a sample of people. A sample of categorical data. 1990, another sample of categorical data. 2000, another sample of categorical data. The difference is we now have more than two samples that we're comparing. And also each one of these samples has more than just a success-failure outcome, right? Each individual from 1980 has 4 choices instead of just 2 choices, success-failure. Same thing with 1990 and 2000. So these are all the differences between this test and a two-proportion z-test. Otherwise, though, it's very similar in the sense that we're comparing samples of proportions, and we are trying to see if they're the same or if they're different. All right, so that's the idea. Now I want to make it clear how this sample was obtained. So there's a population that exists of all graduating classes. And what the people that obtained the data did was they dove in, they specified really 3 particular graduating classes that they were interested in: 1980, 1990, 2000. And notice these are just subsets of the entire population of all graduating classes. And they pulled a random sample from 1980 of 453 people. From 1990, a random sample of 290 people. Even though it's not explicitly stated, I'll tell you that it is a random sample. And from 2000, a random sample of 315 people. Right, so we went ahead and we identified the people that existed that graduated in 1980, and we sampled from there. We identified the people that graduated in 1990, sampled from there, and we did the same thing for 2000. All right, so let's talk about the hypotheses that we're going to set up. So what we are going to do, we're trying to really see, when the term homogeneity, it means same. We're trying to see if the distributions are the same. The distribution of decisions are the same for 1980, 1990, and 2000. Okay? And that's actually, believe it or not, what we are going to assume. We're going to assume that the distributions of decisions are homogeneous. And I know I'm going to spell this wrong. Among graduating classes. So we're saying that the distribution of proportions are the same. That's just like assuming in a two-sample t-test, that's just like assuming that P1 is equal to P2, right? We're assuming that things are the same, and it's up to us to see if there's evidence that is provided that says that the distributions are not homogeneous, or in other words, heterogeneous. So let me pause this and write that out so you don't have to see me writing this whole time. All right, welcome back. And the alternative hypothesis looks similar, except I used the word heterogeneous instead of homogeneous. So we're assuming they're the same, whereas we're trying to prove they are different, all right? And this is, again, called the chi-squared test of homogeneity. Right, and let's just, for the sake of it, say that we're going to set alpha to be 0.05. I'm not going to go through the conditions. I'll point you to the textbook. You can read the textbook for that. But if you've been paying attention, then I'm sure you can guess as to what the conditions are going to be able to use this test. All right, so let's just get into the mechanics of the test. So here is the data. Now, we have to somehow use the null hypothesis, right? We're assuming that the true population distributions of 1980, 1990, and 2000 are the same. What we're looking at, though, are samples. And just because the samples aren't necessarily exactly the same, that, of course, doesn't prove anything. That's called sampling variability. So we're going to go along with the assumption that the distributions are the same. That being the case, in order to get a sense, assuming that all the distributions are the same, in order to get a sense of the true proportion that choose college year after year, the true proportion that choose employment year after year, so on and so forth, we want the best possible sample, or the largest possible sample, in order to get an approximation for those values. And since we're assuming that 1980s distribution is the same as 1990s is the same as 2000s, the best way to estimate the true distribution of decisions is to pool all of that data together. So we're going to use these totals columns in order to calculate the proportions of college decisions for college grads, the proportion of employment decisions for college grads, so on and so forth. So I'm going to take a moment and calculate those proportions now. All right, welcome back. So I filled out the proportions based on the totals. So I took 853 and divided by 1058, 139 divided by 1058, so on and so forth. And there you see these proportions. So now these are sample proportions, of course. They're pooled proportions. And again, I'm able to pool this data together because I'm assuming that the distributions of decisions are the same. These are currently our best approximations for the true proportions. We don't know what the actual true proportions are, but these are our best approximations. A good way to check that you calculated these proportions correctly is to, you guessed it, sum them together and see that they sum to 1, or at least close to 1. There might be a little bit of rounding errors, but you want something very, very close to 1. All right, so now you see below here the same table, but blank, except for the totals. So this top table is what I'm going to call the observed table. And this bottom table is going to be what I call the expected. And this should make sense because remember, the chi-squared test stat, as we discussed yesterday, is the sum of all of the observed values minus their expected values squared divided by expected. And that is true for all chi-squared tests. It's just a matter of, how do you go about calculating the expected values? I'd like you to take a moment and try to guess how you might calculate the expected 1980 college. Now we're looking for counts here, not proportions. We're looking for counts. Based on the data that we're looking at, based on the null hypothesis, what should we expect to be the count for 1980 college decisions and 1980 employment decisions, so on and so forth. So take a moment and, oops. I assure you that's not the answer. All right, take a moment and think about it. Okay, so assuming you have thought about it, the way that you're going to go about doing this is you're going to take, so this is specifically for 1980 college. You're going to take the total from 1980, 453, and you're going to multiply it by our best estimate for the proportion of people that choose college, right? So you're going to take that 453 and divide it by 80.62. And you're going to get your, whatever value you get, you're going to write here. And that is what we should have expected. Out of 453 people in 1980, we should expect that 80.62% of them chose college. 13.14% of them chose employment, 3.97% chose military, and 2.27% chose travel. And that's the same for 1990 and 2000. The only thing that is changing between these values is there are different totals for each year, so we need to take those into account. All right, oops, once again, I assure you that's not the answer. All right, so we're gonna go ahead and fill these out. And once I do that, I will be back. All right, welcome back. So I filled out the expected values. I want you to notice that expected values can be decimal, right? Even though realistically, if we were counting the number of 1980s grads that chose college, there would obviously be an integer. But when we're calculating expected values and averages, things like these, it's okay for them to be non-integer, even if the context in reality calls for integers. Also, of course, you should probably be a little bit more accurate. In other words, go to a higher decimal place, but this is just for illustration. So I only went to the nearest tenth. So again, this value 365.2, just to be explicit about how I calculated it, I took the 80.62, which is our best estimate of overall college decisions, and I multiplied it by the total people that were in our 1980s sample, right? And so that should be what the number of people that we expected to choose college in 1980, and very similar for the rest of those. All right, so now we have our observed data, we have our expected data. Now all we need to do is calculate this chi-squared value for each. Oh yeah, by the way, notice the totals column doesn't really matter. You could use it to check that what you've done, that you've done your calculations correct. So even though each expected count in 1980 is different from the observed counts, they should still sum to 453. Similar, the college rows should sum to 853, and the employment row, or all the values in the employment row, should sum to 139. So that's one way you could use the totals column. Otherwise, it doesn't really come into play. Now, what I'm going to do is take each one of my corresponding observed and expected values, and I'm going to plug them into this formula right here: observed minus expected squared divided by expected. So we're going to get a table full of chi-squared values, and then we're going to sum them together in order to get the chi-squared test statistic. So once again, please give me a moment while I go ahead and do that. Welcome back. That took a while. Just to, again, to be clear, this is the table. Oops. Okay, so this is the table of chi-squared values. So each cell has its own value. And remember, each cell was calculated. So this 4.6 was calculated by taking the observed 2000 college. So that's 288, minus the expected 2000 college count, which is 254, squaring that, and then again dividing by expected. So each individual cell was calculated by taking the corresponding observed and expected, putting them into that formula. Now, so that's the individual chi-squared values. Notice totals don't matter. I'm just actually interested in the actual variables themselves. So now that each term has a chi-squared value, I can now calculate the test stat, which is, in this case, the chi-squared test statistic, which is just the sum of all the numbers in this cell. And this sum happens to be 73. Now, I do want to really emphasize the fact that I am only rounding to the nearest tenth. Realistically, to get a more accurate calculation of this test stat, you want to go to probably 3 or 4 decimal places for your expected value table and then your chi-squared value table. But just for illustration purposes, I went to the nearest tenth, and it just so happened that we got an integer value for our chi-squared test stat. All right, well, now comes the fun part, the p-value. What is the probability of observing our chi-squared test stat or more extreme? And remember, in the case of a chi-squared distribution, the values range from 0 to infinity. So when we say or more extreme, it's always or greater than. So to calculate our p-value, we wonder what's the probability of calculating chi-squared greater than or equal to 73 in this case. Now, if you watched the chi-squared goodness of fit test video, you might be saying, What about degrees of freedom? And indeed, you're correct. Degrees of freedom does come into play, right? Because is the value 73 large or small? Well, that really depends on how many numbers we're adding together. In this case, we're adding 12 numbers together to get a 73. So 73 might seem pretty high. However, if we were adding 3,000 numbers together to get a 73, then 73 might not seem very high. So we do need to take into account the number of numbers that we're adding. And in a situation like this with the chi-squared test of homogeneity, degrees of freedom is equal to the number of rows minus 1 times the number of columns minus 1. And this is excluding the totals columns. So in this particular case, the number of rows is 4. So 4 minus 1 is 3. And the number of columns is 3. So 3 minus 1 is 2. So our degrees of freedom in this case is going to be 6. So that is going to be important information when we go ahead and calculate our p-value. So let's do that now using our trusty TI Smart View. So we are going to do second distribution, chi-squared CDF, of course. Oops. This is from yesterday. So let's see, what is my lower bound? 73. My upper bound again is going to be some large number, 9999 suffices. And my degrees of freedom in this case are 6. Paste, enter, something extremely close to 0. So let's just say essentially 0. All right, of course, you're going to compare this to alpha to make your decision on whether or not to reject H null and whether or not we have evidence to support the alternative. So I'll leave that up to you. But there are a couple of things that I want to discuss before this video is over. There's a shortcut, of course, right? Because this would be a heck of a lot of work in order to do all these calculations by hand. So I'm going to show you the very wonderful calculator shortcut in order to do all this. I also want to point out that after you look at your table of chi-squared values, let's use a different color. Yeah, this guy right here, this table of chi-squared values, you can kind of get a sense for which values, which I guess cells are really different from what we expected. So for example, if you decide to reject the null hypothesis, which is of course going to be the decision we make here with such a small p-value, the follow-up question for the chi-squared test of homogeneity and also the chi-squared test of independence is, what category had the largest influence on your decision? And so you might answer that question in this particular case by saying the 1980 employment and the 2000 employment decisions were had the largest chi-squared values and therefore seem to have had the highest impact on our decision. Okay, in the next video, I will talk about residuals because residuals is a thing in this hypothesis test. But it's very similar to kind of what I discussed, except instead of looking at the chi-squared values, we look at the signed distance away from expected. So in other words, you can look at the residuals and be able to understand if we are below what was expected or above what was expected. But again, we'll go into more details in the next video on residuals. So the shortcut, which is I'm sure what you're all interested in, we're going to make use of matrices. So take out your calculators and the first thing you're going to do is press second and then matrix. And you're going to get a list of different matrices. They're just labeled with letters. What we're going to do is scroll over to edit, and we're going to input the information from our observed table. Now, matrices are described, or one way of describing a matrix is by the size or the dimensions. And it always goes rows by columns. So if you look back to our observed table, and again, we're ignoring totals. We're just interested in the actual values of the two variables. And the two variables, of course, are year of graduation and decision made. There are 4 rows and 3 columns. So in here, I'm going to type in 4 and then 3. And then you could see that the table that appeared, or the matrix that appeared on your screen, now has 4 rows and 3 columns. And now you just simply input the data. So 320, all right. So I'm going to pause, input the data, and I'll be back. All right, so as you can see, I entered all of the observed data into matrix A. I'm now going to quit out of that screen, and I'm going to go to stat, tests, and all the way at the, or near the bottom, you'll see something that says chi-squared test, and everyone should have this. So this is as simple as could be. Once you've entered your data into your observed matrix, you're going to just choose a matrix to be your expected. You don't have to enter anything into matrix B. The calculator is going to do that for you after you calculate, after you press the calculate button. So we're just saying that, all right, the calculator is going to paste the expected numbers into matrix B. Enter, and look what it does. It calculates our chi-squared test stat. It calculates our p-value. It calculates our degrees of freedom. And again, their chi-squared test stat is more accurate because they went to like 10 decimal places. But you can see that we were close, 73. Our p-value was essentially 0, so is theirs. And of course, our degrees of freedom were the same. But the cool thing is that they actually do all of those calculations for you. And bonus, if you go to second matrix and now scroll over to edit, this way you can view matrix B, and scroll down to matrix B, press enter. You'll now notice that they actually went ahead and pasted the expected table into matrix B. And just to sort of verify, look at this 365.23, very similar to the 365.2 that we have in that corresponding cell. All right, they of course just have it to more decimal places. So there you have it, ladies and gentlemen. That is the chi-squared test of homogeneity. In this case, we end up rejecting the null hypothesis. We have evidence to support the claim that the distributions of decisions are heterogeneous among graduating classes. In other words, things have changed. As decades go on, the decision-making process after high school changes. All right, and that's probably something that really, it makes sense from decade to decade. As the world changes, decisions change. All right, hope you enjoyed. Next video, we'll talk about chi-squared test of independence, which is very, very, very similar. I mean, nearly identical to what we just discussed today. And we'll also maybe get into residuals a little bit. All right, folks, have a good day.